Hello students, welcome to the complete tour of chromatography. In this chapter, we will explore the fundamentals and various techniques of chromatography. Chromatography is a physical method of separation where components are distributed between a stationary phase and a mobile phase that moves in a definite direction. The term chromatography comes from Greek words meaning color and to write. It was invented by Mikhail Tsvet in 1906 to separate plant pigments, leading to the colorful bands that inspired the name. Chromatography can be classified based on the nature of the stationary and mobile phases, as well as the instruments used. Examples include gas-solid, gas-liquid, and liquid-liquid chromatography. Further classifications include thin-layer chromatography, gas chromatography, high-performance liquid chromatography, and more, each with unique methods and applications. Chromatography can also be classified based on the principle of separation, such as adsorption, partition, ion exchange, affinity, and chiral chromatography. There are various chromatographic techniques including thin layer, high performance, ion exchange, column, gas, and gel chromatography, each with specific uses. Different techniques involve different stationary and mobile phases, such as solid, liquid, or gas, which affect the separation process. Thin layer chromatography, TLC, is a simple, fast, and cost-effective method used for qualitative and quantitative analysis to separate organic compounds. TLC works on the principle of adsorption chromatography, where components with less affinity towards the stationary phase travel faster, allowing for separation and analysis. In TLC, the choice of stationary phase is crucial for effective separation. Factors like chemical composition, particle size, and morphology must be considered. The mobile phase in TLC is chosen based on empirical rules and the nature of the compounds. It often involves a mixture of solvents to optimize separation. Chromatoplates are prepared using glass or flexible plates coated with adsorbent. The method of application can vary, including pouring, dipping, spraying, and spreading. Adsorbent is applied to plates using techniques like pouring, dipping, spraying, or spreading. Commercial spreaders ensure uniform layers for effective separation. After application, plates are dried and activated by heating. The solvent system dissolves substances, transports them, and ensures adequate separation. The choice of mobile phase depends on factors like the nature of the substance, stationary phase, and mode of chromatography. Solvents of varying polarity are used for effective separation. Solvents should be stored properly to maintain their effectiveness. Some solvents can be kept for months, while others need specific conditions to remain stable. Solvents vary in polarity, affecting their use in chromatography. Examples include hexane, toluene, acetone, and water, each with increasing polarity. Samples are applied to TLC plates using a nonpolar solvent. The process involves drawing guidelines, dissolving the sample, and spotting it on the plate for analysis. Running a TLC involves preparing the developing container, preparing the plate, spotting the sample, developing the plate, and visualizing the spots for analysis. To prepare the TLC plate, start by pouring, dipping, spraying, or spreading the adsorbent. TLC plates are typically 5 cm by 20 cm sheets, cut into smaller plates. Handle the plates carefully to avoid disturbing the coating. Draw a line 1/2 cm from the bottom to mark the origin. Lightly mark the spots for samples, ensuring enough space between them. Prepare a 1% solution of the drug in a volatile solvent. Dip the microcap or micropipette into the solution and spot it on the TLC plate. Allow the spot to become dry before repeating. The example plate has 3 different quantities of the same solution. Place the prepared TLC plate in the developing beaker and cover it. Allow the plate to develop until the solvent front is about 1/2 cm from the top. Remove the plate and mark the solvent front with a pencil. To visualize the spots, circle any colored spots lightly with a pencil. Most samples need to be visualized with a UV lamp. Hold the UV lamp over the plate and circle any spots you see. Wear goggles and gloves for protection. TLC developing chambers can be ascending, descending, or horizontal. Vertical development involves solvent and liquid vapor equilibrium, adsorption, and migration. Horizontal development involves placing the HPTLC plate face down in a glass plate sandwich configuration. The reservoir holds the developing solvent, and the cover plate and conditioning tray complete the setup. This method offers better control of operating conditions and allows for developing both sides of the plate, doubling the sample capacity. Thin layer chromatograms can be developed in 1 or 2 dimensions. One-dimensional development includes vertical, horizontal, circular, and anti-circular methods. Multiple development involves separate runs over the same distance or stepwise increasing solvent strength. Two-dimensional development uses one solvent system for each dimension, with separation in the first dimension followed by chemical reaction separation in the second. One-dimensional development is common but often yields less quantitative results. Two-dimensional development offers more complete separation by using different mobile phases in each dimension. This method enhances separation and provides better results. TLC is used for analyzing natural products, checking the purity of samples, and identifying organic compounds. It is also used for checking distillation fractions, separating cations, and analyzing amino acids. TLC is valuable in both qualitative and quantitative analysis. High-performance thin layer chromatography, HPTLC, is an advanced form of TLC. It is used for both qualitative and quantitative analysis, offering visual chromatograms and multiple sample handling. HPTLC is efficient, with reduced analysis time and higher resolution due to smaller particle size. The principle of TLC involves separation by adsorption. The mobile phase flows by capillary action, and components move according to their affinities to the adsorbent. Components with higher affinity travel slowly, while those with lesser affinity travel faster, resulting in separation based on affinity and solubility. TLC and HPTLC differ in several parameters, including plate usage, layer thickness, sample application, and efficiency. HPTLC offers automated application, higher efficiency, and reduced analysis time compared to TLC. The steps in HPTLC include sample preparation, selection of the chromatographic layer, pre-washing, conditioning, sample application, mobile phase, chromatographic development, detection of spots, and scanning and documentation. The HPTLC process involves selecting the chromatographic layer, pre-washing and preconditioning the layer, applying the sample, preparing standards, optimizing the mobile phase, developing the chromatogram, detecting spots, and scanning and documenting the chromatoplate. The validation process in HPTLC includes method selection, optimization, stability, specificity, precision, and robustness. These steps ensure the analytical goal is achieved with accuracy and reliability. Sample preparation for normal phase chromatography uses silica gel or alumina pre-coated plates and nonpolar solvents. Pre-washing removes water vapors and impurities. Conditioning involves activating plates in an oven at 120 degrees Celsius for 15 to 20 minutes. Sample application in HPTLC involves applying 1.0 to 5 microliters of the sample using Linomat or automatic applicators. The concentration of applied samples ranges from 0.1 to 1 microgram per microliter. Manual and semi-automatic applicators are also used for precise application. The Nanomat is suitable for conventional TLC plates, HPTLC plates, and TLC and HPTLC sheets. Semi-automatic sample applicators require an operator, while automatic sample applicators allow precise application of large volumes. ATS allows overspotting without damaging the layer. Chromatographic development can be ascending, descending, horizontal, continuous, gradient, or multidimensional. Common problems include tailing and diffusion. The twin trough chamber offers low solvent consumption and reproducible pre-equilibrium with solvent vapor. The automatic developing chamber, ADC, automates the development process, ensuring consistent results. Detection of spots can be done by iodine vapor or UV light. Scanning and documentation involve scanning the HPTLC plates and converting bands into peaks for analysis. The detector in HPTLC consists of various components, including a lamp selector, entrance lens slit, and photodiode. Factors affecting HPTLC include the type of stationary phase, mobile phase, layer thickness, temperature, and sample amount. HPTLC has applications in the pharmaceutical industry for quality control and purity testing, food analysis, clinical applications, industrial applications, forensic investigations, biomedical analysis, environmental analysis, cosmetics, and natural products analysis. Column chromatography is a versatile method for separating mixtures of compounds. It involves a solid stationary phase and a liquid mobile phase. Adsorbents like silica and alumina are commonly used in column chromatography. The choice of stationary phase is crucial for effective separation. Mobile phases act as solvents and developers in chromatography. Their selection is based on their ability to dissolve and transport compounds. Columns support the stationary phase and their dimensions affect separation efficiency. The length and diameter ratio is important for optimal performance. Preparing the column involves packing it with an adsorbent. Proper packing techniques ensure efficient separation and prevent air bubbles. Wet packing involves slurrying the adsorbent with solvent. The sample is introduced and separated based on its interaction with the mobile phase. Detection of components involves collecting and analyzing fractions. Factors like particle size and temperature affect column efficiency. Column chromatography is used for separating mixtures, purifying compounds, and isolating active constituents. It has both advantages and disadvantages. Ion exchange chromatography separates ions based on their charge. It involves cation and anion exchange processes using specific resins. Ion exchange resins are classified based on their type, chemical nature, and structure. Each type has specific properties and applications. The apparatus for ion exchange chromatography includes columns and resins. The stationary phase and sample preparation are crucial for effective separation. Mobile phases in ion exchange chromatography are aqueous solutions. Buffers control the pH and sample preparation ensures proper separation. Wet packing is ideal for ion exchange chromatography. Development and analysis of the chromatogram are done using various techniques. Regeneration of ion exchange resins involves treating them with acids or bases. Batch and column methods are used for this process. Ion exchange techniques include frontal analysis, displacement development, and elution development. Each technique has specific applications. Chromatographic parameters like rate of ion exchange, flow rate, and mechanical strength affect the separation process. Swelling and particle size are also important. Factors like surface area, porosity, and selectivity influence ion exchange. Cross-linking in resins enhances their strength and capacity. Resolution in ion exchange chromatography is affected by various factors including the nature of ions and resins, temperature, and column length. Ion exchange chromatography has diverse applications including water analysis, metal separation, and biochemical compound purification. With we come to an end of chromatography chapter 1. I hope you like this video. Hey, goodbye, see you in chapter 2.